Good morning friends, I hope you are doing well. I request everyone to watch my videos in a sequence for better understanding. In this video, we will discuss about minimization of a DFA. Till now we have directly constructed minimized DFA, all these things. Suppose they have given a DFA, how can we minimize it into a smaller DFA? We will discuss it. Now as I discussed earlier, for a long ways L1, any long ways if you take, you can construct n number of DFAs. You can have DFA 1, DFA 2, you can have DFA 3, so on. You can have n number of DFAs. For a given long ways, you can have n number of DFAs. So from the n number of DFAs, you can minimize and it make it into one minimized DFA, M1. Let me make it as M1. Okay, for a given long ways, you can have n number of DFAs. For the n number of DFAs, you can make it into one minimized DFA. So that's what from starting I am saying that for a given long ways L1, you will have only one minimized DFA. Whereas you can have n number of DFAs. But however, you will have only one minimized DFA. So we will identify what is the minimized DFA for any given DFA. Is it clear? What is meant by minimization? We are reducing the number of states in the DFA, because for storing each state we will take some space. So if I reduce the number of states, then the number of transitions also will reduce, so I can reduce the space complexity. Okay, so to reduce the space we will go for the minimization of DFA. Now let me read the procedure how we will do the minimization. First we will reduce the number of dead states, or ideally you should make it into one dead state. Okay, you should make ideally one dead state. Now can you tell me what is meant by dead state? Till now we have discussed so many examples. Let's take that there is a state A, there is a state B. We have written on A what is happening, on B it is going to a state D, A comma B. Like that we have represent something. Okay, on here A comma B is there. We will not discuss what it is. Now I want to discuss what is a dead state. Now if you see that A, from a state capital A, on small a you are going to the B, which is a final state, and initial state is A here. Now capital A on B you are going to a state called D. On A and B you are still staying in the D. Now I can call the state D as a dead state or a trap state. Why I can call is that from the state D you cannot reach the final state. Okay, if you see that, can you reach from D to B? No, you cannot reach it. Is it clear? You cannot reach to A, you cannot reach to the B. If you can reach to the A, then you would have reached to the B, because there is a connection between the state A to state B. However, you cannot reach from D to A. So I can say that a state which is called, when we will call it as a dead state, is from that state you cannot reach to the any of the final state. Meaning in this example you have only one final state called B, but in some examples you may have more than one final state. So that's why we call it as a set of final states. If you cannot reach any one of the final state, then that state we will call it as a dead state. Now if you have more than one dead state, what is the use? You will make it into only one dead state, so that you can reduce the number of dead states, which is internally making as number of states reduction. So we will try to reduce the number of dead states, and ideally means if possible. If it is possible, we will make it into 0 dead states, but if it is not possible, we will at least make it into one dead state. But some DFAs may not have the dead states. In that case, the number of dead states are 0. If you have in the given DFA, you have more than one dead state, then you should make it into one dead state. With an examples we will discuss, don't worry. Now next step is we will eliminate the unreachable states. What is meant by unreachable state is that, let's take that state A is there, or instead of state A, let me write that you have a Q0 state and Q1 state is there. Q0 is the initial state and Q2 is the state. Now if you see that you have a final state, this one, initial state is this one, Q2 is represented like this. Now what is the initial state in this one? Q0 is the initial state, Q1 is the final state. Now what is meant by unreachable state? From initial state, if you cannot reach any state, that state we will call it as a unreachable state. Let me repeat again. From the initial state, if you cannot reach any state, that state we will call it as a unreachable state. Now in this one, if you see that from Q0, you can reach Q1. Am I right? But from Q0, can you reach Q2? No, you cannot reach. However, from Q2 to you can reach Q0. But my point is that from initial state, can you reach this state Q2? No, you cannot reach Q2 from Q0. So we will call this Q2 as unreachable state. So these unreachable states are waste of us, because if you are generating the long ways, these states are not useful for us. So we will eliminate the unreachable states. Now the next one is that we will identify the equivalent states. Okay, first whenever they have given the DFA, first we will do these two things, reduce the dead states and eliminate the unreachable states. Then we will try to identify the equivalent sets. Now when I can say that two sets are equivalent or two states are equivalent is that there, let's take that I have state 1, I have a state 2. Now state 1 on input alphabet A and state 2 on input alphabet A, if they are going to some non-final state. Is it clear? Let me repeat again. State 1 on A, state 2 on A, if they are going to a non-final state, then I can say that they are equivalent. Meaning is that lot of people will think like this. S1 of A, state 1 on input alphabet A, state 2 on input alphabet A, both are going to state 3, some state 3, then we will call it as equivalent. But that is not correct. The correct one is that you have a final state and non-final states. So if state 1 on A is going to some non-final state, state 2 on A also should go to some non-final state. Then we will call it as state 1 and state 2 are equivalent. Okay, what is that equivalent? We will discuss later. Okay, whether it is 0 equivalent or 1 equivalent, all these things we will discuss. Now let me repeat again. Now state 1 on B, state 2 on B, if state 1 on B is going to some final state, state 2 on B also going to some final state, then we will call they are equivalent. Okay, so I hope you have understood. Let me repeat again. Two states on taking the same alphabet, if they are going to some non-final state, if it is going to some other non-final state and it is going to some other non-final state, then no problem, they are equivalent. Is it clear? Are you able to understand? But if it is going to some non-final state, let's take that. If S1 on C, it is going to non-final state, S2 on C is going to a final state, then we will call they are not equivalent. Is it clear? Now let me discuss about what is zeros equivalent, 1 equivalent, all these things. Now let me discuss in a simple way. S1 on W, S2 on W. S1 on W is going to a non-final state. S2 on W is going to some non-final state. Then we will call, just now we discussed that they are equivalent. Is it clear? S1 on W, some alphabet W, S2 on W, if you are going to a non-final state, we will call them as equivalent. Now when I can call them as 0 equivalent or 1 equivalent or 2 equivalent is that it depends on the length of this W. Is it clear? If the length of this W is 0, then I will call them as 0 equivalent. If length of this W is equivalent to 1, then I will call them they are 1 equivalent. If W of 2 is 2, W means length of the W is 2, then we will call them as 2 equivalent. Okay. So we will discuss about the steps in reducing the DFA. Okay. Let me discuss about the steps in minimizing the DFA using equivalence method. What is the step 1? All the states are divided into two partitions. The partition 1 consists of set of final states and another partition consists of non-final states. So it will be represented as P0. So if you consider any DFA, you will have a final states and non-final states. So this set of states you will divide into two partitions. One consists of set of non-final states and another one is set of final states, and assign some k is equal to 0. You take some constant k and assign it to 0 so that we can represent it as P0. Now in step 2, increment the k value by 1. Initially you have taken k is equal to 0. Now k value will become 1. When you are doing the step 2 for first time, k value will be 1. For each iteration, for each partition in pk, divide the states in pk into two partitions if they are k distinguishable. We have discussed about what is 1 equivalent, what is 0 equivalent, all these things. So here they are saying that k distinguishable means when k value is 1, you will call it as 1 distinguishable, meaning is that 1 equivalent. Okay. Now read this step 3. If pk not equal to pk minus 1, meaning is that, suppose let's take that I am doing p1. Next time if I am doing p2. So p1 and p2 I will check whether they are equivalent or not equivalent. If they are not equivalent, then repeat the step 2. Okay. Else go to step 4, because any algorithm or any procedure you should have a termination condition, otherwise it will go for an infinite loop. So what is the termination condition is, if any two partition, means in 1 equivalent and 2 equivalent, if they are same, you cannot further divide, then you will stop the procedure of minimization. Is it clear? Or if they are not same, then again we will do the step 2. So that's what it was written. If pk is not equivalent to pk minus 1 to the previous step, then repeat step 2. Okay. Else go to step 4, meaning is that if they are equivalent, if the two 0 equivalent and 1 equivalent are equal, then we will say that it is done and we will stop the procedure. Now when we will, means after stopping, what we will do, combine the kth equivalent sets and make them the new states in reduced DFA. Because let's take that you have six states are there and you have found that 2 states are equivalent. Is it clear? That is what the objective is. Out of 6 states, let me write here, you have 6 states are there. Out of the 6 states, you have identified 2 states are equivalent. If 2 states are equivalent, you will combine them and you will make it into 1 state. Then how many states will be there? Only 5 states will be there. So with those 5 states, you will construct the new reduced DFA. Let me repeat again. In the original DFA, let's consider that you have 6 states, and using this procedure, you have identified that among 6 states, 2 states are equivalent. If 2 states are equivalent, you will combine them and you will make it as a 1 state. That is what our objective. Okay. If you combine them in the 2 states into 1, then totally you will have 5 states only. With those 5 states, you will construct the new reduced DFA. So that is what the algorithm or the steps in the minimizing the DFA. So I hope you have understood how to minimize the DFA. In the next video, I will discuss this concept with an examples for better understanding. Thank you so much.